In this problem, we're tasked with creating a function that determines whether or not a context-free grammar is infinite. We say an infinite grammar is one that accepts an infinite number of strings. So let's come up with an example. Here's a grammar that accepts strings that spell out ba, different lengths of a, 3 a's, and this can be possibly an infinite number of a's that follow the b. An example of a finite grammar, I simply took the infinite grammar, removed the a right here, and this grammar only accepts the string b. Since the number of strings that this grammar accepts is finite, it's not infinite, it's not an infinite grammar. So before I go on with how we're going to approach this problem, I'm going to go over one of the assumptions that you were given in the problem specification. And that assumption is that for every non-terminal in the grammar, it derives at least one non-empty, that's critical, string. If you see S, you can assume that there's at least one non-empty string that S derives. So how does that help us? The way we're going to approach this problem is that we're going to try to see if we can rewrite Q, where Q is any non-terminal in our grammar, in the form of some terminal X, Q again, and some terminal Y, where either X or Y is non-empty. That is, the length of X and Y together is greater than 0. So they both can't be empty, because that's not a very helpful rule. If Q goes to Q, it's not going to make us any progress. The reason that this is important is that if we have this rule, or can rewrite Q in this form, we're back to the ba rule that we had originally. If we have this rule, we can build up an infinite string by simply repeating it over and over again and adding x's to the beginning or y's to the end. And so that's how we get an infinite grammar. And the assumption comes in again, because if we see this rule, we've assumed that Q can derive at least one non-empty string. We don't have to run what we wrote earlier in the homework, CFG empty on Q. We can just assume it. So I don't actually even have to check if Q can eventually finish. If I find Q, I found that the grammar is infinite as long as this property holds. So let's go over the game plan. I'm going to go through each non-terminal in the grammar, because it doesn't really matter where I start. Any one of them is a valid way to generate an infinite grammar. And then I'm going to check for each of those non-terminals if it's possible to form something in the manner of this rewrite rule. So how do I do this part? I'm going to write a recursive helper function, and I'm going to check if that rule is of that form. If it's not, I'm going to recurse. If it is, I'm going to stop. So let's go to the code. So here I've declared my function, CFG infinite, where I take in a Python representation of the grammar. I'm going to go through every rule in the grammar. That's what this list comprehension does. And Q is going to be the left-hand side symbol in that rule. So this may be new to you. And what I've done is I've declared a function within my function. The effect of this is that I can only call the helper function that I'm creating within the function CFG infinite. One advantage of doing this is that this function is not useful to any other code because I wrote it specifically for CFG infinite. So I can restrict access so that it's not misused in other places or depended on in other places. One disadvantage is that it kind of makes the code harder to read, and it makes it more difficult to understand where functions can be called and where they can't. Regardless, I'm using this helper function to determine whether or not the symbol Q can be rewritten in our form of xqy, where the length of x and y together is greater than 0. The three parameters are the current symbol we're at, the symbols we visited, we don't want to loop around, otherwise the helper function won't finish, and the size of x and y in that case. It's this value. If I've looped around and I've already visited something, I'm going to return whether or not the size of x and y is greater than 0. If it is, we found the rule that we're looking for, and the helper will return true. If it's not, we're going to return false, because we're not making the progress towards an infinite number of strings that we wanted to. Otherwise, we're going to have to parse through the rewrite rules that apply to that symbol current. I'm going to update my list of visited symbols, and then I'm going to go through each rewrite rule. So here, this for loop iterates through the right-hand sides of every rewrite rule that the current symbol applies to. Where the current symbol is equal to the left-hand side of that rule, it returns the right-hand side. Just another way to say it. I'm going to go through every symbol on the right-hand side, and I'm going to recurse on that symbol. Where the current of the recursive call is the symbol I'm on, I'm updated symbols I visited, and I'm updating the size of x and y that was passed in before with the length of the right-hand side minus 1. We do the minus 1 to exclude what we're recurring on, the q. In this case, q is symbol. When I do prove that q can go back to q, I can then check the size of everything else that I found before I found that loop. If helper is never true, then I'm just going to return false. So now that I've defined my helper function, I need to use it. So for each symbol q, which this list comprehension returns, I'm going to try my helper function on that symbol. If that's ever true, I'm going to return true. If for every symbol I never find the helper function to be true, I'm going to return false. And I'm done.